Okay, I think I'm recording this now. So I'm going to try to keep my face out of the way over here. My thought process on this, and I'm hoping that you had the opportunity to do this part. I didn't talk about this today, but to find total resistance, we've got parallel resistors connected to each other. You're going to have to use that 1 over total resistance equation. And I didn't show all the work here, but after you go through all the steps, and I did not find a common denominator. You could, but I just typed in the reciprocal of 25 plus the reciprocal of 33 equals, and I took the reciprocal of that answer. I showed that in a video like weeks ago, but there are calculator methods you can do there. I'm hoping 14.2 works out. I'm hoping that's an answer that people were getting, okay? I don't know if... I was going to try to do a thumbs up, thumbs down thing, but I'm just going to keep this off to the side here. So 14.2 ohms is what I end up getting for the left side of this circuit. That's in series with 60 ohms, so that should give us the total resistance of like 74.2 ohms. All right, so from there, now that we know the total voltage is the voltage of your battery, this is always going to be the biggest voltage of your entire circuit is the battery itself. We've got the total resistance. We should be able to solve for total current. Okay, V equals IR is my main equation. If I divide both sides by R, V divided by R should give you a current. And I got about 0.16-ish amps. I rounded it to 0.162. I think 3 decimals is fine. If you just did 2 decimals, that's fine also. I'm just trying to give you the indication if you're doing this properly or not. And now my thought process here is, how do I fill in the rest of this? All right, so what I want to say is anytime you've got a single resistor sitting all by itself, you're going to get all the current going through there. Because even though current leaves the battery and splits up, it's all going to come back together here, and all of it will go through the 60 ohm resistor. So that's the comment that I've got here next. Total current goes through the single resistor in series, 0.162 amps right there. So now you look at the picture. Okay, we've got a picture here with a current going through a resistor. Current times resistance. Current times resistance should give us voltage. So we can fill in these 2 cells right here. Here's the current going through the 60 ohm resistor. If we multiply current times resistance, we'll get the voltage across that resistor. Okay? So now the next part that comes up from there is once we know the voltage across here, I want to kind of think about what do we know about voltage in a series circuit. Okay? Let me see. If we were to draw in these wires with some colors, and we were to show my highest voltage wires and my lowest voltage wires, some in-between voltage wire. I should have done that green, but I did it orange instead. The method we can go through here is to label each wire. All right, this is a 12-volt battery. It means there's a 12-volt difference from red to blue. So you've got 12-volt red wire. The entire red wire is that same high voltage. You've got a 0-volt blue wire. That entire blue wire is the same low voltage. And then we've got some in-between voltage. It's not always exactly halfway between here. In this case, it's going to be some number, any number between 0 and 12 is what we should expect to see. But specifically, let's say 9.7 is what we should be anticipating here. Okay, why is that? The way I justify that is because if I put a voltmeter across this resistor, okay, that voltmeter is going to show you a difference. The difference between this wire, orange, and this wire, blue, okay, is going to give you that 9.7 volt difference. Oops. Okay. Oh boy. There we go. All right. So from there, now that we've identified these different wires, now we should be able to look at well, what's the voltage difference going to be across the red-orange wires. You've got a 12-volt wire here, 9.7-volt wire. It just comes down to the difference. Okay. Subtract 12 minus 9.7, and we should be good to go. Okay, does that come out 2.3? And I know I'm rounding a little bit here, but hopefully these are close enough to what you've got. Okay, so that's the thought process on this. And once you've got the voltage for a given resistor, you can solve for current. You've got voltage for this given resistor, you can solve for current. And notice, I better back up and say this. The voltmeter, it looks like I'm only measuring the 25 ohm resistor, but anywhere you see a red wire, you could put this voltmeter test lead here and this voltmeter test lead here. That's still red-orange. Same color difference means same voltage difference. In fact, I could take this test lead and connect to some metal down here. Take this test lead and connect some metal over here. That's still going to give you 12 minus 9.7 for your voltage difference. Okay. So let's go on from there. I think I show next, yeah, voltage divided by resistance should allow you to solve for current. Pretty sure I rounded that, but hopefully that's close enough to be familiar. Each of these values should be the currents that you have. And then, you know what, I'm going to leave power to you. Power is current times voltage right in there. So that would basically get you through page 8 and page 9. If I could, though, allow me to take a couple of minutes to show you one more method. Okay, now, if you understand what we did and you don't want to watch any more of this, sit tight for a couple minutes. But this, I feel like, might help with the next pages that come up. Okay, page 10 and 11, particularly page 11, the strategy that I want to show you now will give us the same answers. So here's the punchline is we're going to get these same answers right in here, but I just want to show you a different method because sometimes we may not just have 3 different voltage wires to deal with. We might have more than just those 3. All right, so bear with me for a couple minutes here. Let me go to another slide here. Oh, here, I forgot about this. Current in these 2 parallel resistors add up to the current coming out of the battery, okay? You can just double check that. Okay, let me go to this other method. Okay, I won't take too long on this, but consider this for a minute. If you could, where are we at here? Sorry, my screen is, there we go. It's kind of freezing up my PowerPoint. Recall the total resistance of the parallel part. Think back to over here. I'm hoping you wrote that number down. What was the total resistance of this? You can say it out loud to yourself if you want. Pretty sure this was 14.2 ohms. Okay. What if we replaced, sorry guys. What if we replaced those 2 resistors with a 14.2 ohm resistor? Okay. Basically my thought is that we'd still have the same total resistance for the circuit. 14.2 ohms in series with 60 would give us the number we already calculated. It's still connected to a 12-volt battery, so we'd still get the same current, right? I guess my question is, if we still have the same totals in this, could you picture how much of that 0.162 amps would go through this single resistor? Well, we already answered that over here. How much of that total current goes through this single resistor? All of it. I think we could assume that all that current would go through this single resistor if the circuit looked like this instead. Now, I know you might think, well, it's not this circuit. This is just a strategy that might be helpful later on that would allow you to find the voltage from here to here. So just bear with me for another couple clicks, okay? Imagine all that current goes through that one equivalent resistance. That's to say 0.162 amps goes through 14.2 ohms. Can you see that we've got enough information from this modified picture where we could solve for voltage across this modified resistor? Could you take a couple of seconds to try that out? Humor me for just a minute. Take this current going through this resistance to figure out what the voltage is across here. Okay, I'll try to stop talking for about 15 seconds while you grab your calculator. See, I can't even stop. My apologies. Okay, I just counted to like 15, and I don't know if I counted properly or not, but here, let me just interrupt at this point again. My thought is, let's take that current times resistance, right? Current times resistance gives you voltage. And you should come up with 2.3 volts, which we already solved for before. So again, it's a little bit of a spoiler. I already told you that. We solved for 2.3, but here's just another method that you could use. Suppose all that current went through a single resistor that was equivalent resistance to that 25 and 33 ohm resistor that were actually in parallel, okay? So now we're right back where we were. We know this 23 ohm resistor, excuse me, this 2.3 volt difference across these resistors actually exists, okay? We can kind of see how that works out, all right? Now, here's what the picture looks like to me. I always got to kind of picture a voltmeter here. That's basically touching this wire that we colored in red before and connecting to this wire that we colored in orange before. You're just finding that red-orange color difference, which represents 2.3 voltage difference. All right. And again, why'd I do this right down here? I just want to put this little reminder remark. This method should be helpful for the tougher circuits that are yet to come. Like on page 10, 11, this might be a little bit helpful. I don't expect you to do page 10, 11 this week. That's what I'm going to deal with next week. But I want to come back to this method one more time next week and see if that's going to be helpful. Here, let me continue on here. I guess the next step here. I guess the next step is now, well, let's reveal what the picture actually looks like. It doesn't actually have a 14 ohm resistor. It's got a 25 in parallel with 33. Same thing, but now we can evaluate each of these pieces. Okay, so we can figure out the current by taking voltage divided by resistance for each of these. Again, same answers as we had before. Okay, and that basically wraps that problem up. I guess I should go through and do power just so you can kind of check your work. I'll leave that up for a couple seconds. You can take a picture of it if you want, but I'm going to stop the share here in just a minute and head back into the main classroom.